Hey MathHL. So today we are going to look at applications of vectors. So vectors allow us a way to write the equations of lines that have specific spots for the x component, the y component, and the z component if there is one. And that means that it's a really good way to model the movement of something. In our examples, we are only going to model linear movement, things moving along the line. As you progress further in math, you'll be able to model movement that's doing more than that. Things might be moving in a nonlinear way. But just so you know, for what we're doing in this chapter, we're focusing on linear movement. But we can do that now that we have three-dimensional vectors. We can do that in 3 dimensions as well. So we're going to talk about what parts of the vector equation of a line correspond to what, as well as how we can figure out when paths of things will cross and also when objects might collide. And so we'll look at the designation between that. So a couple of specifics. If we see the position vector of the equation of our line in vector form, the position vector is our starting point. The direction vector is equivalent to velocity. When you're working with velocity vectors, you do not want to simplify them from how they are written, how they're given to you. So for example, if you get a velocity vector that's 6, 8, you do not want to simplify that to 3, 4, because you'd be changing the velocity. So that's a difference from what we worked with before. Normally, we could simplify a direction vector from something like 6, 8 to 3, 4. But when we're doing application, we're not going to do that. So that's one note that's a little different than how we've worked with these before. And then if they ever ask you for speed, it's just the magnitude of the velocity vector. Okay, let's jump into an example. We've got a two-dimensional example to start with. On a sunny day, two sailing boats, Rab and Pag, were spotted from a lighthouse. The courses of the boats Rab and Pag from the moment they were spotted can be given by these two equations. So we have equation R and equation P. Now, I want you to notice that they do not have it written as the position vector plus the parameter times direction vector. They actually have it kind of mixed up from what we're used to. But we can actually change that ourselves. So what we can do is this. We can say, well, the position vector are the numbers without the parameter. So -1 and 10. And then we have our parameter t. And then we have the direction vectors 2, -2. Like I said before, we actually do not want to simplify this to 1, -1. We would then be changing the velocity. We'd be making it slower. We don't want to do that. We want to preserve the size of our velocity vector. Now for P, there is no I value that doesn't have the parameter S. So that just means that the starting position is 0. And then 4 plus S, 2, 3. So whatever's with the S goes as our velocity vector. Okay, so now that we've rewritten them in a form that we're more used to, let's continue on. We have kilometers and time in hours. Okay, part A. Find the positions of the boats when they were spotted and the distance between them. From the moment they were spotted is when these start. So that would be equivalent to t equals 0 and s equals 0. We are assuming that they're spotted at the same time. They don't specifically say that, but we kind of have to assume that. So if I substitute in a 0 for t, I'm going to get that I'm at the point -110, right? -110 plus 0 is -110. That's where Rab is. If I substitute 0 in here, I'll get 0, 4. That's where Pag is. And now I want the distance, so I can just use the distance formula. I subtract my x components, square them, subtract my y components, square them. So I'm going to get 1 plus 6 squared, so 36. So rad 37 kilometers. If you wanted to make that a decimal, you can. Make sure you preserve 3 sig figs if you do that. So we could also write 6.08 kilometers. That would be so we have our positions here and here, and we have our distance here. Part B, calculate the speed of each sailing boat. So the speed is just going to be the magnitude of our velocity vector. So we're going to take our 2, -2, and find the magnitude of that. So we get rad 8. So simplified radical form would be 2 radical 2. Again, feel free to make that into a decimal if you prefer. That would be about 2.83 kilometers per hour. That would be our speed for, this is RAB. No, this is RAB. And then PAG, we would simply repeat the process. So we have a 2 squared and 3 squared. So 4 and 9, so rad 13, which would be approximately 3.61 kilometers per hour. So those are our speeds. Part C. Find the coordinates of the point where the courses meet. So at this point, I'm going to pause actually, and I'm going to do a little diagram just so we can kind of see what's going on a little bit more. I'm going to make an X and Y axis here. Just so we can visualize this a bit. It doesn't ask us to do this, but we certainly can. So let's first plot where each of these boats are at t = 0. So this first one is at -110. My scale is just by 1. -1, 1, 2, 3, 4, 5, 6, 7, 10. So that is rab. And then 0, 4 is pag. Now we can also model their movement as well. After 1 second, I am going right 2 down 2. So at t = 1, I'm going to be right here. So that's the movement after 1 unit of time. What is our unit of time? Hours. So after 1 hour, now rab is right here. And so I can just continue doing that and show where I'm at a couple different times. So after 2 hours, after 3 hours, this would be after 0 hours, after 4 hours. Oops, 4 hours. And I can do the same thing with PAG. And this one has right 2 up 3. Right 2 up 3. So it looks like our intersection point is going to be right there, whatever that point is. That seems to be where, well, actually, it's not an intersection point. We'll talk about that. The paths cross. The path of PAG and the path of RAB intersect at that point there. Okay, so this little drawing sort of shows the movement of each boat. So after 1 hour, RAB is here and PAG is here. And then they continue going in their respective directions in the same pattern. So, C, find the coordinates of the point where the courses meet. One approach would be to graph it. So we'd have 2, 1, 2, 3, 4, 5, 6, 7, 2, 7. So if you're able to graph it, if it's reasonable enough to graph, then you can totally do that. However, a lot of these are going to have values that are so large, graphing it's not going to work. So how do I find where their courses meet? Well, that's the same thing as saying, where's the intersection of those lines? Well, we know how to do that. We can set the x components equal to each other. So the x components, and we can set the y components equal to each other. And now we can solve. If I add straight down, I get 9 equals 4 plus 5s. And so s equals 1. To find out where the location is, where they meet, I simply plug in s equals 1 to the PAG equation here. So I'm going to get 2, 3. Or no, not 2, 3. I'm going to get 2 and then 4 plus 3, so 2, 7. So the same answer either way, whether you use a graphical approach, if that's possible for the problem, or we can use an algebraic approach like we see here. So 2 comma 7. Part D, explain why the boats will not collide. Well, to explain, I think I'm going to plug in a 1 for S, and I'll do the first equation here, and then solve for T. So I'm going to add that 1 second over. So T is 1.5. These are both times, and we started both of them at the same time. So at 1 hour after the starting time, RAB was at 2 comma 7. But PAG wasn't there until 1.5 hours. So they both were in the same location, but they weren't there at the same time. So because they were not there at the same time, they are not colliding. So RAB is at 2 comma 7 after 1 hour, while PAG is at 2 comma 7 after 1.5 hours. So they will not collide. So their paths cross at 2 comma 7, but they don't actually collide because they're not there at the same time. That's how you figure out if there's a collision or not. Okay, so we've looked at a 2-dimensional example. Let's look at a 3-dimensional example. Okay. When you're dealing with a 3-dimensional example, right, we have an X, we have a Y, and we have a Z that's going up. That's usually the way it is. X and Y usually are flat on your paper, and Z would be vertical. They don't always do it that way, though. Occasionally, they'll make the Y component height instead of the Z component. So you don't want to assume it's automatically the Z component. You want to use context clues to help you determine that for sure. So if you read through the problem and you look at your equations carefully, you can probably tell which one is which. So let's look as an example at this example. Irma and Ida have 2 drones that are flying at a constant speed. Irma's drone starts first and takes the path described by the equation given by L1 here. So line 1 is 2i minus 3j plus the parameter t times negative 2i plus 3j plus 4k. After 3 seconds, Ida's drone starts and takes the path described by the equation given by line 2 here, negative 4i plus 2j plus the parameter s times negative 2i plus 4j plus 7k. Take a look at my position vector, which is where we begin. At t equals 0 and at s equals 0, I'm at 2 comma negative 3 comma 0. We're in 3 dimensions here, so we have to have a third component. But notice that there isn't a third component listed for our position vector. That just means it's 0. So 2 comma negative 3 comma 0. So ijk, so the k component is 0. So that means it's logical that k would be the height. That the z, the third component, z, is going to be the height. Because where would a drone start? On the ground. And so at the starting time, it would have a height of 0. So because of the context that you see in the equations, it's reasonable to say that z is height because of those things. Okay. We are measuring distances in meters and time in seconds this time. Firstly, find the speed of each drone. Well, we know that that's just going to be the magnitude of the direction vector. You can see that they are grouped the way we're used to. We have the position vector, and then we have the direction vector with the parameter each time. We should label, this is Irma. So we're going to get 4 plus 9 plus 16, which is going to be the square root of 29, which will be, I worked this out ahead of time, so I don't have to waste a bunch of time. doing that. Oh, maybe I don't have that handy. Okay, well, I'll recalculate it. Square root of 29, about 5.89. Sorry, 5.39. And this will be meters per second. Okay, and then IDA. Same process, but I use IDA's direction vector, -2 squared plus 4 squared plus 7 squared. So I'll get the square root of 69, I believe, yes, which is approximately 8.31 meters per second. So we can see that Ida's drone is going more quickly than Irma's drone. Part B, determine the distance between the two drones just before Ida's drone starts. Now, if you picked up on this when we were reading the question, Ida's drone starts 3 seconds after Ida's, after Irma's. So Irma's starts, and then 3 seconds later, Ida's starts. So if we want the distance between them just right as Ida's drone is starting, that means we're going to plug in t equals 3 for Irma's equation and t equals 0 for Ida's. Because Irma's already 3 seconds in to her drone's path, whereas Ida's is just about to start. So that little detail was important. So we can plug in a 3 and see where Irma's is. I'm going to rewrite mine as vertical. So 2, -3, 0 plus t, -2, 3, 4. I'm going to plug in t equals 3 here. So the position of Irma's drone is going to be 2 minus 6, -3 plus 9, and 0 plus 12. And now for Ida's, I'll do the same thing. I'll plug in a 0 for Ida's. So if I'm plugging in a 0, the XYZ value is just going to be -4, 2, 0. So these are the XYZ locations, right? The locations in 3 dimensions of each drone. And then I can just find the distance between them by using our handy dandy distance formula. Notice these are the same, so those will just end up being 0 when I subtract them. You could jump right to that step. So the distance between them, I'm going to get -4 squared and then 12 squared. So 16 and 144. So the square root of 160, we get about 12.6 meters. This is a distance, so just meters here. So that's how far apart Irma's drone and Ida's drone are, just right as Ida's drone is going to start. Part C, the drones will collide. So they're telling us they collide. For how long was Irma's drone flying when they collide? So I want to know Irma's time when they collide. So I know that they're going to cross paths. So I can just set the x components equal and the z components equal and the y components equal, whichever two you want, and see how that turns out. So I'll have 2 minus 2t equals -2 minus 4s. -3 plus 3t equals 2 plus 4s. And then 4t equals 7s. So I can cancel out one of my parameters here. I think I'm going to multiply this one by 2. Keep that one the same. And then I'll get 1 minus t equals -6. So I'll get 7 equals t. T is for whose drone? Irma's drone, right? Irma's drone starts first and takes the path described by the equation. So, 7 seconds after Irma's drone begins is when they will collide. Now, normally, we don't know when they give us two equations, two three-dimensional vector equations, we have to find the t and the s and plug them in to make sure that the x, y, and z are all equal. The reason we don't have to do that here is because they tell us they collide. They're not asking us to determine if they collide, they're saying that they do. So we can work on that assumption. And we can just say that Irma's drone was flying 7 seconds when they collide, because Irma's was first, right? Irma's was first and it has the T. Okay, so yes, 7 seconds. D, find the altitude. Altitude's a fancy name for height, right? Find the height where the drones collide. Well, if I take my Z component for Irma, I can just merely plug in 7 to get the height. So that'll be 28, and we are in meters. So that would be the height that the drones are at when they collide. Unfortunate. Those are expensive. Okay, so that's how you can approach questions where they're having you talk about applications of vectors. And that's it for this video.